In this video, I'm going to go over the derivation of charging of a capacitor. Let's begin. So the end derivation, or the end formula, or the end function is what you see on the screen. What this formula tells us is that the amount of charge is equal to the capacitance. So remember, the capacitance tells us like how much the capacitor can hold in terms of charge. And here we have this is EMF, okay, or the voltage, times 1 minus e to the negative t over RC, where t is time, R is the resistor or the resistance for the circuit, and C is the capacitance of the capacitor itself. All right, so it's nice to know where we will end up in our derivation journey. So let's begin. The first thing I want to start off with is the RC circuit itself. And so let's start off with a EMF source, and we're going to link that up to a resistor, and that resistor will also be linked up to a capacitor like so. Okay, and so here we have the EMF source of E. This is the resistor R, and this is a capacitor of C. So what we're going to do is we're going to start off with Kirchhoff's loop rule to come up with our starting formula. So I'm going to start down here in the lower left-hand corner. Okay, I'm going to go up, 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 and the first thing I'm going to hit is this EMF source. So we have EMF, and then it's because we're going from a negative to a positive, that EMF source is going to be positive, and then we're going to go around, go around, go around. We're going to hit that resistor, and remember, for this formula, we're trying to write down all of the voltages. And see, the voltage for resistor will be R times I. Okay. Notice there, I made the I lowercase. And the reason why I made that lowercase is that in differential calculus, whenever you have a changing variable, you want to make it lowercase. If it were a constant, you will want to make that a uppercase. Okay? And so because the current is changing as the capacitor is being charged up, we're making that a lowercase. So we're going to keep on going, and then we're going to hit that capacitor. And the formula for capacitance would be minus Q over C, or Q over C is the capacitance formula. And once again, that Q is going to be lowercase because the amount of charge changes as time moves on. All right, so this is the derivation. Let's finish off the loop first. There we go. All right, so there's nothing else in the circuit, so this is our formula. Okay, so if this is our starting derivation, we want to get to an endpoint that tells us how much charge is on the capacitor as time continues. So let's begin. The first thing that we want to do is we want to identify the different substitutions that we can use. One of them is current. So current we know to be dq over dt. So this is the amount of charge that is flowing per unit of time. And so with that, actually begins our journey. So let's begin. We get EMF minus R times dq over dt minus q over c. Okay, and remember, our end result, we want to function in terms of q of t, right? Q of t. So we want to make sure that every variable with a q in it, we make on one side, and every other variable to be on the other side. And so let's just do a little bit of algebraic manipulation. So we get, let's see here, I'm going to say EMF is equal to R dq over dt plus q over c. Only reason why I'm doing this is I want to get rid of all my negatives first. Then I'm going to subtract the q over c on the other side. Okay, now that I see that, right? I could have left it there, but I'm just doing everything all at once. Next thing I want to do is I want to divide everything by R. And the reason why I want to divide everything by R is because I want just dq dt by itself. And so we get epsilon R divided by q over c divided by R. Okay, and this is equal to dq over dt. All right. Yeah. And so what we get here is we can do a little bit of rearranging, I believe. So we know that epsilon over R is current, and this is initial current. So I'm going to leave that as I. Okay, minus, let's identify what the constants are here. So the constants are R over R and C. So what we're going to do is we're going to set a constant to replace that constant, simply because I don't want to work with anything in the denominator. So K would equal 1 over RC. So this formula becomes QK is equal to dQ over dt. Now that's just a mathematical trick, simply to get rid of that RC in the denominator, and to replace my constants with another constant. It just makes my math a little bit cleaner. Okay, so the next thing I want to do is I want to make everything with a Q together. So here, this is a term that I don't want to separate. Okay, so we get dt is equal to dq over I minus qk. And at this point, what we can do is we can take our integral. But before we take our integral, let's set a u substitution. So I'm going to say u is equal to I minus qk, and du is equal to, so that I, because it's capitalized, it is a constant. So the derivative of a constant just gives us nothing. So we get negative k dq. Now the helpful thing about this is that we have that dq here, and we have the dq here, so that's part of our substitution. And the other substitution is the one that we created ourselves. We have this this phrase here, which we're going to substitute into that denominator there. And so with all the substitutions, we get dt is equal to negative 1 over k du over u. And now we can take the integral of both sides. And so when we take the integral of both sides, remember, it's important to know what you're deriving, or what you're taking the integral of. Okay, and so the idea is that at time of 0 seconds, and remember, this is for charging up, at time of 0 seconds, the amount of charge on the capacitor will be 0. At time of infinity seconds, the amount of charge on the capacitor is what we just call Q total, right? And we'll just say that's just Q, I don't know, QF, Q final. All right, so let's make this from 0 to t. So we get t is equal to, and the integral of this will be negative 1 over k times the natural log of u, and then we have our bounds. So right here, I'm going to substitute back in my u so that I don't have to worry about creating my bounds in terms of u. And so that'll give me negative 1 over k, natural log of, what do we make u? We made u I minus qk. So we have I minus qk, absolute value, and then we have that integral there. Oops. Excuse me. So our bounds, our starting amount of charge is 0, and our end amount of charge is Q final. All right, or Q total. So at this point, I'm going to substitute in my bounds into my integral. So we get negative 1 over k, the natural log of I minus q final k. I'm just going to leave that in terms of q, minus the natural log of I. Okay, and all of this is being multiplied by negative 1 over k, and this is equal to time. All right, and so we have the natural log in my brackets there, and whenever you subtract two natural logs together, you're just dividing the natural logs. And so I'm going to do two steps in once. I'm going to get that negative 1 over k over on the negative side. So we get negative kt is equal to the natural log of I minus qk divided by I. All right, and so at this point, what I want to do is I want to raise everything with respect to e to get rid of that natural log. And so what ends up happening is we get negative kt is equal to I minus qk over I. All right, so this here, I want to reduce this as much as possible for future sake. And so we get I divided by I minus qk divided by I, and this just turns into 1 minus qk divided by I, and all that is equal to e to the negative k qkt power. All right, and so what I want to do is I want to clean this up a little bit. So we have this term here and this term here after everything was simplified. And so we get e to the negative kt power minus 1 equals negative qk over I. And once again, we're trying to solve this in terms of our variable q, right? So that's what we're looking for, the q final, or how much q can exist at any moment of time. And so we want to rearrange this algebraically so that we get q is equal to. So what I'm going to do is I'm going to multiply both sides by this k over I, but the negative k over I, and I'll highlight that here in green. So I'm going to multiply both sides by that, and what ends up happening is we get q is equal to 1 over, or excuse me, I over k, and let me make sure if I distribute out that negative, we get 1 minus e to the negative kt power. All right, so at this point, what we can do is we can resubstitute back in that k, and let's see what we made that k. We made k, going back, 1 over rc, okay? And so we get q is equal to I over 1 over rc, and this just turns into IRC times 1 minus e to the t times 1 over RC. So that gives us RC like so. All right, now we're almost there. The N formula has a EMF function in it, and we see here Ohm's law, where EMF is equal to IR right there. And so all we got to do is substitute back in EMF times C is equal to, or times 1 minus e to the negative t divided by RC. And there we go. We found the amount of charge that will be on a capacitor as time continues. So this is the end derivation for a charge or charging of a capacitor. So what we need to be able to do is to be able to create graphs from this, right? So when t is equal to 0, what we said is that the total amount of charge on the capacitor is going to be 0, right? There's nothing flowing yet. So let's see if this holds true. So we get, we'll do it over here where t is equal to 0, epsilon c 1 minus e to the 0th times the absolute value, or times the bracket of that. And so this gives us 1 minus 1, and that gives us 0. 0 times EC, Q does in fact equal 0 coulombs at time 0. And what about at time infinity? We said at time infinity, the capacitor is going to be fully charged, and so the amount of charge is going to be just the total amount of Q, or just Q final, right? And so let's see if we get that. And so we get Q is equal to epsilon capacitance 1 minus e to the negative infinity power, and the negative infinity power just gives us 0, so this gives us Q is equal to EC, right? And from here, you're like, wait a minute, Lee, I thought you said it should be Q final. But remember, the formula for capacitance will be charge per delta V, right? And if we substitute that in there, we get, let me show you the substitution, that C with this C here, we get the EMF times Q over delta V. And this delta V is simply the EMF, and that cancels out. And so we get Q is equal to the Q total. And remember what I said in calculus, whenever you have a lowercase, that's the variable or the changing variable. When you have an uppercase, it's the constant amount. So we got it. What about charge and a graph? So if we take a look at charge per time, okay, so this is charging up a capacitor. At the beginning, we know that the total amount of charge will be 0, so down here, and at the end, the capacitor is going to be fully charged up over there, and it has a horizontal asymptote, right? And so the question is, what should that equal to? And that'll just be the total amount of charge, Q, right there. Q, and that Q just comes from the substitution that we did before, where Q is just going to be, let me just make sure, this is going to be the capacitance times the EMF, all right? Okay, now with the amount of charge per time, we can also infer the amount of current flowing per unit of time, okay? And we know that at the very, very beginning, the amount of current that is flowing is at its max. So we have that up here. And over time, as that capacitor is being fully charged, it acts as a back EMF or almost like a resistor. And so the current approaches 0. So we get a value that looks like this, like so. And the question is, what is that maximum amount of current? And from there, we can just use Ohm's law, where V is equal to IR, but that current would be I is equal to V over R, but we got to use the variables that we know. So the EMF divided by whatever that value of resistor is, that would be the max amount of current. Okay, so one of the things that you'll be expected to do is know how to create a charge versus time and a current versus time graph based on your scenario. Okay, so one last thing I want to leave you off with is that this should remind you of the air resistance formula, the derivation, and it's very, very similar, where in air resistance, the velocity was being reduced as timing continued, but for this one, the amount of charge building up is being reduced as time continues. So it's almost identical in nature. All right, I'll see you next time. Bye-bye.